And we have the grand partition function for non-localized. For non-localized, you will get, you remember it was the exponential of the z, q1. Exponential of the z, v, I'm substituting this here. Again, you have this number here, 2mp over h. So can I write it as some parameter c, for example? Beta minus 3 over 2. So exponentially zv constant over t3 over 2. So this is the question. So it's maybe you are not aware about the importance of these equations. I will inform you now what is the application of this. When you have a partition function, you know you can calculate everything, so like the average of the particle, like anything. So I want just to write some things, like for example, if you consider the case of the non-local, so you can write the average of the particle minus 1 the cube on the alpha. We needed to remember, we call it this equation, and this will be zv, a function of the time, t. This. We write just for the particle which is non-relativistic, you see? Because always I use the p square over 2m, but you can have any function of the p, You can have any function of it. So generally, so that will be something like zvft, because this is only for the non-relativistic, when the Hamiltonian is just p over 2m. But not necessarily that. You can have any function of momentum as the kinetic energy. So you can find the average of the particle, and you can find the many parameters. But what is the example? The example which I want to study is a system with two phases. Solid gas system. You have a metal sheet, and here you have the vapor of some kind of the gas, like uranium, for example. Uranium, or any other gas. So you set this metal surface, and in your in your system, for example, you have a part of the metal is in the contact with a gas is with heavy elements like uranium. I write uranium because it's very heavy. You can write any other things. So it should be some type of the thermodynamical process between these two materials, And it should be some kind of the equilibrium also here. Equilibrium means that after some time the system will reach a fixed temperature and a fixed pressure and a fixed chemical potential. Three conditions for the equilibrium. You remember T1 should be equal to T, P1 equal to P2, and mu1 equal to the mu2. Three type of the equilibrium. And what is I want to find the pressure of the system after the system becomes in the equilibrium. It's very important because you needed that, because with this you can consider some mechanism to control the pressure, for example. Because I told you this type of the things are very important in industry actually. You needed to have you have to be able to control the pressure of this system. Anyway, you need to find the pressure. You need to find the pressure when the systems reach equilibrium. And you will see that it will reduce to that. Why? Because I can consider the vapor as a system of the free particles. So this is a non-localized system. And because you have the full pattern or full picture of the system, so you need to consider the system in grand canonical. I mean, you know this is a chemical element, this is a chemical element, like the metal. Any chemical element have the chemical potential, So if you consider the system in the canonical, you lost a part of the information about the chemical potential. So you need to consider the type of the enzyme when you have the chemical potential. This is the grand canonical. So you need to consider the grand canonical enzyme instead of the because it requires to have the full picture of the equilibrium. Full picture is satisfied by Therese equation. We know that we use always this as an equilibrium before canonical line. But when you have a metal, when you have the material, when you have something with internal structure, so you needed to check also the chemical potential. Everything has chemical potentials according to the conservation of attention. And pressure, because definitely it should have some pressure. So I will start the calculations and you can continue that. So because I want to give this as a homework to you, but you can find it in the book. So in the textbook you can find it. I want to extend this calculation. Anyway, what model for the metal I can use? There is no any model for the metal actually. Nobody knows that what's the real type of the metal, how it works. Just we know that there are some atoms here, and these atoms have they have normally the interaction like the Coulomb interactions, And the best structure for the metal is that when the system becomes in the mechanical equilibrium. I mean, all the atoms has a small oscillation near the equilibrium points. So what you remember that? What I say to you is that exactly that you can consider the system as a harmonic oscillator. Just as approximation. So the Hamiltonian for the metal, I write the Hamiltonian of the single harmonic oscillator. And you know that that can be block of the metal. So you can consider the problem in 3 dimensions, or you can consider just in 2 dimensions because it's very this size you can forget about that and you consider it. For me it's the same. I put the vector here, okay? So we can consider 1-dimensional even. It's just wire. One wire. So you put a wire near to a material like with the heavy elements like the uranium, like anything, thorium or the Kurchatvium or uranium is